the recording. So last time we talked about the construction of response spectral for a given earthquake record. So typically, the earthquake record is obtained based on the ground acceleration. So you will have the time history of the ground acceleration at any given site. So, for example, in California, there is a network composed of, I would say, maybe thousands of accelerometers installed on foundation of buildings or even on the open air ground there. So that a lot of earthquake records can be obtained during a lot of earthquakes, because earthquakes are very active in California. So that we should be able to get one of the acceleration record that you can see on the top of this slope over here. So for any given earthquake load, we should be able to do analysis on one structure. And so, for example, if we have a frame with a rigid floor, if we know the natural frequency, if we select the natural frequency of that structure, we should be able to analyze the structure under the given earthquake, so that we can have the time history of the displacement of the floor Based on the time history, we should be able to tell what is the maximum displacement. So that is the maximum response for a given or for a selected natural frequency equal to 0.5 seconds, for example. So that's the one of the results over here. So basically, we can select multiple values for the natural frequency of the structure. For example, if we have natural frequency equal to 1 second, 2 seconds, so the response will be a little bit different. So the maximum response will be different. Right? So our goal is to obtain the relationship between the maximum displacement and the natural frequency of the structure. So if we select adequate number of natural frequency, we should be able to get a curve like this. So with the variation of the natural frequency of that frame, the maximum displacement of that frame under the given earthquake should be different. So we should be able to get a curve like this. So actually, the response spectral just tells us the relationship between the maximum response versus the natural frequency of the structure. So that is a definition of the response spectrum over here. And any questions before we move forward? And then okay, so some of you have already started your project. I believe when you start doing your project, you will have a much more opportunity to work with this conception, as well as to develop the skill of data analysis here. So this is a definition of response spectrum. And the last time we also talked about the other two types of response spectrum. So initially, we are concerned about the displacement, but sometimes we also need to know the response of velocity as well as acceleration of the system there. But as long as we have the displacement response spectrum, we should be able to get the pseudo velocity as well as the pseudo acceleration response spectrum very quickly, and if we know the natural frequency, because there is a relationship between the velocity response spectrum and the displacement response spectrum. We just multiply the natural angular frequency over here so that we can get the velocity response spectrum. Similarly for the acceleration, and we can just go ahead and multiply by the square of the angular natural frequency over here, so that we can have the zero acceleration and response spectrum. So typically, when we do design, we in that case we should be able to show the three spectral in the same graph, so that we will have a tripartite response spectrum of this card. And today we will talk about so firstly, now it's pretty straightforward for us to get the response spectrum for displacement. So we have the S sub D. While the zero, so this is a displacement. So while the zero, and this is the zero velocity. So there is a relationship between the zero velocity and the displacement. So now we take the log on both sides. And the log. And similarly for the zero acceleration, and we know that zero acceleration that's equal to omega n times zero velocity. So similarly, you can get that. So as you can see here, in both equations, so we can tell that the velocity actually is linear, has linear relationship to the acceleration as well as to the displacement in log sense. We have the, so this is a so these two relationships are typically called the linear relationship. So because of this, the relationship, actually, we should be able to show the three response spectral with the same curve, in the same chart. So for example, so if this is the response spectral for the zero velocity, so by using the same curve, we just use a different axis. Just use the same different y-axis. So those two y-axis will have a degree equal to 45 degrees to the s sub v over here. So using the same chart or using the same data points, we should be able to, if the natural frequency of the structure is given, we can get the response for displacement, acceleration, as well as the velocity at the same time. Right? So, for example, if we give a Tn over here, over here. So this is a SV value, and for the
You need to scroll up a little bit.
oh, okay. So thank you. So if we have the T value over here, we should be able to get the SV from the y-axis, or the vertical y-axis. And similarly, we should be able to get the SA on this axis, and then we get the SD on the other axis at the same time. So typically, that's why usually we have the three different response spectral on the same chart. So, for example, let me show you a quick example here. So online students, can you see the PowerPoint slides on your WebEx?
Yeah, I can see it.
Okay, thank you. So, for example, this is a net response spectral for L central ground motion. So, if actually, if you take structural dynamics courses, and if you do seismic design, I think everybody is very lot of L central is one of the most popular earthquake record name, L central, because the first earthquake record was recorded in L central a small town close to San Diego in California. So that's why a lot of textbooks, a lot of engineering guidelines, we use Ellison program because this is the human history. This is the first earthquake record obtained, recorded by human beings. So we use Air Central over here. And a few years ago, I visited San Diego, and I did not visit Air Central, but there is on the highway there is an exit to the city of Air Central, a very very famous city in earthquake engineering field over here. So as you can see here, typically the response pixel will be given with the x-axis as the natural frequency of the structure, right? And the y-axis, typically the vertical y-axis is zero velocity, and so that this axis is giving us zero acceleration. This one is giving us deformation. So with the same chart, for example, for the L central, if the T is equal to 1 second, and there are 1, 2, 3, 4, 5 different curves. I believe the different curve corresponds to the different damping ratio. Right? So typically, when you use the response spectrum, if the damping ratio is given to you equal to 1%, and if the natural frequency equal to 1 second, we should be able to use the response spectrum here to quickly tell what is the maximum displacement for your structure, without any calculation, So we have the natural frequency equal to natural period, equal to 1 second, so that the deformation should be. This should be, and damping ratio equal to 0.0, and this should be 0.02. This means 2%. So that in this case, we should be able to get the one value from this curve. So this data point corresponds to the response of your structure. So in order to tell the zero velocity, we just so this is the zero velocity value, value. Similarly, we should be able to get the displacement somewhere here. So this is the displacement value. And here, this is the acceleration value, zero acceleration value. Very convenient for us to tell the response of the structure in terms of displacement, velocity, as well as the acceleration very quickly, as long as we have the spectral data. So that's why in the project, I require all of you are able to construct the response vector similar to this. So your final results should be very close to this one, and even you have a different earthquake record. So the pattern would be very similar to this. So increases to the peak and decreases if you have the variation for the natural period of the structure. So if you see something different from this, you need to double check your results, or your program there. So that's the response spectrum for a given earthquake record. So any questions? Okay, please, John. Yes.
How do you determine where to place the SASD origin?
Okay, very good question. How can we tell where to place those axes? So very good question. So for example, there is a relationship. There is a relationship over here. Very good. So as you can see here, that's where we will use those two equations. Right. So as long as we have a sub V over here. So for example, given a sub V value, we should be able to calculate the corresponding SA value. Yeah. So for example, if you would like to, actually these two axes can be placed anywhere in this chart, but when you change the location of these two axes, the numbers will be changed. The numbers on these two axes will be changed because these numbers are dependent. For example, the number at the bottom over here is a function of the frequency as well as the number over here. So actually this number is calculated based on the SW value as well as zero period value over here, based on that equation. And if you calculate this number, you should be able to get all the number on that axis. Similarly for the SA axis, for the SA axis. Make sense? So that's any other questions here? Very good question. Very good. So yeah, when I was in school, it took me a while to figure out how to place these two axes. Actually, you can place them anywhere, but with the location of them changing, and the numbers on these two axes will be changed. But in your project, you are only required to provide the Euler acceleration response or displacement response spectral there. One of them. So okay, so any questions from online students? Are you guys in good shape? So it's Barrington, what's your question? Or you say you are in good shape. Right? Okay, so now let's talk about the procedure to make a response spectrum. So that is very important. So this is a standardized procedure. I believe using this procedure, you should be able to complete your project. So the first step here is you need an earthquake record because one spectral is specifically calculated for one given earthquake. I have already given you the earthquake record in terms of acceleration and considered there. And the next step is you need to vary the natural period of the structure. Natural period. So typically we vary the natural period between 0.02 seconds to 50 seconds. The structure with a very small natural frequency, a natural period, and a structure with a very large natural period. So for example, when you will have a very small natural period, for example, the speed rate of the structure is very high. In that case, the natural period will be very small. For example, if you have a very short span bridge, the short span bridge typically has a very small natural period. And if you have the bridge with a very large span, for example, you have a suspension bridge, such as the George Washington Bridge. So then I believe the natural frequency of that bridge is much higher than the very short span symphony supported girder bridge of there. So that's why we need to know the response of structures with different natural periods here. This is the second step. The third step, we need to find that response displacement, the displacement. How can we get the displacement of the structure? We need to do dynamic analysis using the numerical integration. So we can and using numerical integration, we discussed about 2 weeks ago, we should be able to calculate the response here. So in your homework, I believe you have already also practiced that. It's not a big issue here. And step 4, to find actually the maximum displacement of the UT and is that spectral value. In that case. Step 4, step 5, we should be able to calculate the zero velocity. And similarly, zero acceleration and plot So let's see. So for example, you may select the Tn, the first Tn is equal to 0.02 seconds. And after you are done with that Tn, you need to go to the next Tn. For example, the next Tn equal to 0.1 second, 0.1 second. Right. So how many Tn we need over here? If we would like to have a more precise response vector here, we would like to have as many as possible, but if we use a lot of E7 over here, the calculation will take, we will have much more data here, So that's, so we need to balance, here. So in your project, how would you vary the Tn over here? Would you like to vary the Tn and with equal spacing, or would you if you vary the Tn with equal spacing, what's the spacing you would like to use? 0.1 seconds? So so here I would recommend you to vary the Tn based on log values. You have the equal log spacing other than the linear spacing there. Does that make sense? That means you have the log Tn, you have the log Tn with equal spacing, So that will give you much better results, Because here, as you can see here, the Tn here is varied in the log space, So that's why I would recommend you to use log values for Tn. And so the log values of Tn will be equal spaced, So that will give you much better results. Does that make sense?
I have a quick question.
Yes.
So what's the final graph that we're supposed to have?
The final graph will be very similar to the graph of L central over here.
I can't really see that well.
You cannot
What
see
you're
the
pointing at.
PowerPoint slides?
I can see the slide, but I can't see what you're pointing at physically.
So as you can see here, and I would say your results will be very similar to this curve. So with increasing T7, the values of the spectral are supposed to increase initially, and up to the peak, and then decrease. If you see that type of trend, and that means your results would be your results are correct. If you see a different trend there, then probably you need to check your program, or you need to use better space the T7 over there to get the closer results here. Does that answer your question, Eric?
Kind of, but not really. Are we supposed to have a tripartite graph like this, or are we just gonna have Tn?
No, you are not required to produce the tripartite graph. Okay, you only need to provide either the zero acceleration here or the displacement here as a y-axis here. Either one of them should be okay. You do not have to show the data in the tri-axis graph over here.
All right, because I was gonna say I have no idea how to go about that.
Yeah,
All right, thank you.
welcome. So any other questions? Yes, so please let me know, if you have any questions, about your, project, and, it's due, 19th of April, right? So it's still about, 14 days. So please, make sure, you are on the correct track. Have any questions, please do let me know either by sending me an email or schedule a WebEx meeting with me, or ask me, during the class time, so that we can discuss, make sure you, yeah, yeah, well, you can handle this type of, task, because this is, one of the most important, things in the structured dynamics course. Okay, so that's the construction of the response spectrum over here. So the next one, I would like to show you some, features of the response spectrum curve here. And the application of the response spectrum here. So for example, let me just grab this curve. Save some time here. So actually, there are some, interesting features on the response spectrum. For example, this is the epicentral earthquakes. So for example, if we have take this for example, we consider a structure. With the T7 for 0.02 seconds, right? 0.02 seconds. So if the natural frequency, natural period of the structure is very small, it's equal to 0.02 second over here. So that means, this structure is very steep, right? In the very steep, very steep structure. So do you agree with me? Because the T sub n is equal to 2 pi and n over 8, square root of m. Okay. Since the T sub is very small, that means typically the stiffness is very high. The stiffness is very high. So in this case, if we look at the pseudo acceleration, let me grab another curve that is very important here. Curve. Okay. Then I need the the other term. So as you can see here, this is the Earth ground acceleration chemistry, and on top that's the response spectral here. So as you can see here, what is the maximum acceleration for this earthquake? So it's about 0.4, right? The smaller than 0.4. I would say by inspected all the data, so the maximum here is about 0.32. For example, the maximum here is 0.32 G, 0.32 G. So, and now let's take a look at the response of the structure here. So what is the pseudo acceleration of the structure here? So we have the pseudo acceleration. Should be somewhere here, correct? So we have this 0.2, 0.3. So what's the pseudo acceleration? Is spectral value for the structure if the structure has 0.02 seconds. It's very close to 0.32, 0.32. And S A in this case is about 0.32. So that's equal to the maximum acceleration of the earthquake. So that means if the natural frequency or natural period of the structure is very small, basically the acceleration of the maximum acceleration of the structure is same as the maximum acceleration of the earthquake. So this is a very good feature for you to check your result. So based on your spectral record, you should be able to get the maximum here. And if you get a number close to that, that means that your program is correct. So that's one feature here. And similarly, if we consider another structure with Tn equal to 50 seconds, that means if the period is very large, So what is the displacement of the structure? And the displacement of that structure is so we need to use these points here. Yeah, maybe it's equal to 8.4 something. So this is a very soft. So in this case, the displacement spectral value is equal to the maximum displacement of the ground. So if the structure is very soft, basically the structure moves the same as the ground. We have a very soft structure.
The video on the first day of class with the dinosaur. And like, why did some buildings collapse during the
Yeah.
earthquake? Because their natural frequency was the same as that.
Candle, but they're not
And
But in order to answer your question, why some buildings collapse, we need to do more detailed analysis. This just tells you that if the structure is very soft, the structure moves with the same displacement as the ground, during earthquakes. But that does not necessarily mean the structure will collapse. If you design the structure strong enough, the structure will have very large displacement, but does not necessarily mean it will collapse. Whether it collapses or not depends on whether the required strength, or depends on the demand by the earthquake. Whether the demand by the earthquake is smaller than the capacity of the structure. When we talk about the capacity here, we talk about firstly the strength, secondly the displacement capacity. So when you do earthquake design or seismic design, besides the strength, you also need to consider the displacement capacity. Some structure is very strong, but the structure cannot take the required displacement there. Those structure may also collapse. That's why seismic design is so different from the conventional design. Yeah. In conventional design, you only need to consider the strength. If your nominal, or if the design strength is larger than the required strength, you see that structure should be okay. But in seismic design, that's a different story. So unfortunately for this class, we will not talk about in more details about the displacement design. Displacement design will involve the nonlinear analysis, especially regarding the ductility analysis over here. And here, those responses are only linear responses. Right? We assume all structures are linear in elastic range. But how about the structure and some plastic deformation, such as you have a steel building? Steel building may experience some plastic deformation. So actually, nowadays we design most of the structures on the earthquakes to experience some plastic deformation, such as bridges, columns, and building joints. So all of these parts can experience large deformation, so that we do not need to design very strong, very impractical structures. We can sacrifice some parts of the structure to make sure the structure will be still in good shape under earthquakes. So that's I would say that's why we need that response spectrum, because with the response spectrum, at least for one earthquake, we can tell how it will affect the response of the structure. If the natural frequency of the structure is known, we can quickly get the maximum acceleration, displacement, and the velocity of the structure. So that's the topic about the response spectrum. And let's have a short break, and about 10 minutes. And after that, we will go over an example related to the construction of response spectrum of a given ground motion. And we also will talk about the design spectra that we use the design code. Thank you. Any questions from online students? Okay, if you do not have any questions, I'm going to pause the record.
I thought you usually look at the project like this.
Although, one of my friends.
Well, everyone, let's resume the class. Okay, so example. So now let's say how we can construct the response spectrum to a given earthquake record. So this time we start from the easiest case, So where we have a harmonic ground motion. So the Mother Nature will never give us a harmonic ground motion. But this time let's say what will be the response. How will the response vector of the harmonic ground motion be like in this case? So we have the harmonic ground motion. So the time history of the acceleration can be expressed as the amplitude times the sine 2 pi t over t. So where the t is the frequency of the of it. So part A, we are required to derive equations for the amplitude of the acceleration. And we would like to show what is the relationship between the amplitude of the acceleration with the natural period of the structure as well as the density ratio here. So this is part A. So we are only required to consider the steady state response. So let's say the part A. Part B, we need to show the A and the maximum acceleration identical for undamped system, but different for damped system. So C, we are required to graphically display the two response vector by plotting the normalized values and versus the frequency on the period ratio between the natural frequency of the structure and the natural period of the excitation. So that's a lot of information here, but let's work together to say what So for part A, firstly, we would like to, anytime when we do dynamic analysis, we would like to have the equation of motion. So how will the equation of motion be like in this case? So you have the m times the relative acceleration plus c times the relative velocity plus the c times the relative displacement equal to minus s equal to the times the ground acceleration. That's the equation of motion. So for any First thing. We should be able to have this equation. Should be able to have this. So, any questions regarding this equation? Or I don't agree with, yes,
The R subscript is real, is that
relative. Because, regarding the, ground, movement, we need to use the relative. So here, so the here, so this is the market. So this is a relative acceleration. This is a relative velocity. This is a relative displacement. So now we substitute because ground acceleration here, UGT L here is given to us. It's a harmonic excitation. So that we have with the information, and we should be able to have the so that is so actually or we can write it in terms of natural frequency other than the natural period here. So let's say the equal to where the omega is equal to 2 pi over t. And so we have what omega is the natural frequency, the frequency of the excitation other than the period of the excitation. So here, if you look at this equation, basically on the right side, or the top or the bottom, that's a force. That's a force. That's a force in the form of a sine. So that means we should be able to get the maximum displacement based on the equation that we have before. If you have the textbook, then you should be able to find that equation. So the maximum displacement of the structure should be equal to the amplitude of the force over the stages of the system. So this is the static. So this is the static displacement. The dynamic displacement should be the static displacement times square root 1 minus beta. And that's the equation we used a lot in the first exam. The maximum dynamic response should be equal to the static response times static displacement times the here. Do you agree with me up to here? So
What's that symbol in the middle of the 2 and the beta?
oh, 2 theta, 2 times theta times beta.
On the bottom of the
Yes,
the fraction.
that's a damping ratio. Right.
Okay.
That's a
Thank you.
damping ratio. The damping ratio. Sorry for my handwriting. So now so now we should be able to so the amplitude of the ground acceleration over, so what is m over k? M over k. So that should be the natural period, the natural frequency squared, omega n squared, omega s squared. Times here, and that's the way. Got over s squared. Because beta is a ratio between the natural frequencies, the excitation, and the structure, and the structure. Any questions up to here? It's very simple. So now here, because typically the response spectral is plotted as the maximum response versus the period. So we need to use period here, natural period here, other than the natural frequency here. So we just go ahead and use the change all the ratio of natural periods to change ratio of natural frequency to natural periods. So that's equal to does this make sense? So this is the response values in terms of the ratios of the natural periods and the period of the excitation. So then we should be able to derive the zero acceleration spectral values. So the A value zero acceleration, spectral values should be equal to omega n squared times st. So the zero acceleration is equal to the square of natural frequency times the displacement. So that's equal to the zero acceleration, spectral values, spectral values. Well, the actual acceleration, amplitude. This is the real acceleration amplitude here. That's equal to, yeah, that's also given in your textbook. And the first one, this is a pseudo. This one is the actual. So the actual acceleration amplitude should be rated in this, of course, in this one. Are they the same? Are they identical to each other? Are the zero acceleration and actual acceleration amplitude identical here? They are not. Yeah, they are not. They're not identical. Yeah, because if you look at what's the difference here? So the acceleration, the actual acceleration amplitude has a term there, but the zero one does not have that term. Does not have that. So, but when let's go to part B. We are done with part A. We have already expressed the zero and the actual acceleration amplitude in terms of the ratio of the periods here. The next step we will discuss the case where the zeta equals to 0. If there is no damping, if there is no damping, A is equal to and then the U So that's two. The pseudo one, the actual one, they are identical. So the only one is that NP ratio is equal to 0. This is a part B.
Professor, for the actual, isn't the whole thing square root?
Yes, the whole thing is square, yes. Right. And the whole thing needs to be square root. As you can see there is it's a half order. Half order. Yes, everything needs to be square root. So now let's plot. First thing on is to plot the pseudo one and the actual one in the same spreadsheet to see how much difference there will be over here. And then let's open the spreadsheet here. You have your let's see what will be, how much the difference will be. So here we can include the T over N over T here as the x-axis, and we have the theta, and we have the B value, and then the actual acceleration. Actual acceleration. So here we just normalize the UG0. We just normalize UG0. So we divide the UG0 on both sides. So that we only need to consider the normalized example. We have the T over T and runs from 0.01 with O2. Use a equal log value. And over here we use 0.1 and 1. Let's see what will be the difference here. So if we use theta equal to 0.2, this is B, that should be equal to 1 over the square root of 1 minus plus and 2 times the theta. No. 2 times theta. Ratio here. Ratio here. That's the A value. And we can also get the actual ratio here. And that's equal to square root everything inside. And, anything. So we plot so we would like to use the axis with a different scale. Different scale. For example, we can also have the y-axis. That way we should be able to tell the difference of the pseudo and the actual response over here. So, yes,
If you go over to the A divided by U GO
yes,
and click on that cell that's 1.0001.
yes.
Okay, there is 2 square. Okay. No, I was just making sure my number is a little off.
Okay. Okay.
Thank you.
Actually, this one also shows you how to plot the response spectrum for your project. So you can, after you get the data, you can just show all the data in log and log. You should be able to change the pattern of the axis to plot the log and log values other than the actual values. So because here we only show 5 data points for each of the curve. And if we use more here, the story will be a little bit different here, Such as if we use more data points here, we insert some to get some more precise result here. It's a case where you have more data points. That's not much difference here because we use a very small MP ratio, very small MP ratio. So in your case, for example, you can mark this as MP ratio 0.02. This spreadsheet, MP ratio equals 0.02. If you want to use a different MP ratio, you just copy. Make a copy here. So for example, we would like to change this to 0.1. We just change everything to 0.1. And that's how you can do your project. You can just go ahead and use different sheets here, spreadsheets here to consider different MP ratios. But for the TS, you will also have to have multiple values. Example, if we change this to 0.2, that means the difference between these two will be more. It's an increasing of the damping ratio. The difference between these two terms will be more significant. So this is the response spectrum. This is the pseudo as well as the actual acceleration response spectrum under a harmonic ground acceleration. So the pseudo one is not always equal to the actual one. This example is very important because it tells us why we call the pseudo one the pseudo because it's not the actual term. So any questions up to here? Is everybody negotiate to construct the response spectrum? If the earthquake record is given to you, at least for one selected damping ratio, and if I give you a set of different T values, you should be able to do that. The only difference between this example and your project is these values are not expressed in a closed form, but you need to find out those values based on the numerical integration result here. So it's data to plot the response spectrum. Okay. So if you know any questions, let's talk about the design spectrum. So before we discuss about the design spectrum, I have a question for you. Question here is, so if you are required to design a structure, for example, a building or a bridge in a given location. So if a structure to be designed at a given location, how can we determine the maximum acceleration as well as the maximum displacement under earthquakes? So we have already learned that given a structure, given an earthquake record, we should be able to calculate the maximum displacement and acceleration. Right? So we know that given an earthquake, the displacement and the acceleration can be determined. But when we do design, who will give us the earthquake? When I assign the project, I give you the earthquake. But when you do design, who will give you the earthquake record? It's CE7. But the CE7 does not directly give you the earthquake record, but give you a design spectrum. Right? So where does the design spectrum come from? So this is related to the design philosophy for earthquakes. So for example, for a given location, we can only tell the earthquake. We can only tell the data of earthquakes during past years. For example, in San Diego, California, there might have been signs of earthquakes occurring in the past 80 years, because the first earthquake was recorded about 80 years ago. So in the past 80 years, we know that there are about maybe 1,000 earthquake records there in San Diego, California.
1940, we could have a party.
47.
We could have an El Centro party.
So, for example, for El Centro, the same location in California, there might be 1,000 earthquakes that have happened in the past 80 years. But our structure will be designed for future earthquakes. Right? So among the 1,000 earthquakes, which one will occur in the future? Or we will have a different one from the earthquakes.
Earthquake in the past.
Geologists, like what is possible? Had this in the past, but it was under these conditions, kind of like.
Okay, very good insights here. So Michelle suggests us to use the maximum earthquake event. And Elizabeth suggests us to consult with the geologist about the probability of the earthquakes. I would say Yes, both of you, there's some insights over here. So we show, you suggest us to consider maximum. Maybe that may be too conservative in that case, right? Why? Because in the same location, if you want to design a structure for the maximum structure may only occur once per 50 years or once per 100 years. If you design for that earthquake, your design may be too conservative for some structures. Right? So if you for design a residential building for that earthquake, your design would be very conservative because I believe a lot of residential buildings will not be there after 100 years, especially in California. Yeah. So yes, maybe conservative. So probability, yes, you need to consider the probability. So for different types of structure, you need to consider different levels of earthquakes. For example, for hospitals, schools, or some important infrastructure such as power plant, you may have to consider the maximum. And for some residential buildings with of less importance here, you can consider the lower level of earthquake intensity over there. So that means when we do design, we need to consider the probability. But the probability is only based on the data from past years. So that's how the design spectrum is constructed. So that's why in order to answer this question, we need to find a way to construct the design spectrum. So for example, so for a specific location, we should be able to, if I say this is a acceleration spectral here. So for a given location, we should be able to for a given location, we may have multiple, maybe thousands of different earthquakes. So for example, we have earthquake 1, earthquake 2, blah, blah, up to earthquake number n. Fine. So the number n is dependent on how many earthquake records you have already collected during the past 80 years. So in order to consider all the cases, we will have to consider all the response spectra here. So what is the design spectrum? Right. So design spectrum is smooth. We want to use the smooth. We use a smooth curve to enclose all the response spectrum that we can construct based on the earthquake records on the given location. So that if we have a design spectrum on top of, above all the earthquake response over here, we should be able to, on the safe side, we have already considered the worst case over here. So this is the design spectrum. This is the design spectrum. But when we do design, we have to also consider some, as I mentioned earlier, the level of importance for different types of structures. So for some structures of the highest importance, we need to use the higher design spectrum. And for some structures with lower ones, we need to use lower as design spectrum so that we can consider all the cases here. So let's say what the building code states over here. IEC. So for example, the online students, can you see the PowerPoint slides on your screen here? As you can see here, this is a typical design spectrum that we can plot based on the IBC code or ASA7 code over here. So for different damping ratios, the zero acceleration for your design will be different. The higher the damping ratio, the smaller the acceleration will be. And as you can see here, this is actually all the design spectrum are developed. So the envelope of all the earthquake records for a given site, and for a given soil type, So when you do design, you should be able to figure out what is the maximum equivalent static force you need to consider here. So let's work together on a quick example here. Example from the last years. Let's work together and show an example to see how we can use a design example. The design spectra is typically, as you can see here, is typically smoothened other than the curve spectrum over here. So for example, this is the pseudo acceleration. This is the pseudo acceleration spectral here. And we have the natural frequency on the axis over here. If we have two adjacent buildings, the one building has a height of 5 meters, the other building has a height of 3 meters here. So on the earthquakes, we know both of them 5% that critical of damping. So what is the maximum separation that two buildings needs to be over here, needs to be have over here. So we know that EI over N is given EI over N is given in this case. So what is the maximum separation? Those two buildings needs to be designed. Why we need the separation here? Because under earthquakes, the left building may move to the right, and the right building may move to the left. Right? So the gap will be closed. A little bit over here. So we wanted to make sure there is no collision between those two buildings. So that means we need to find out the maximum displacement of these two buildings under the design earthquake. And the design earthquake is given as the design spectrum. The design spectrum is the envelope of all possible earthquakes considered on that site. So how should we do in this case? So any suggestions? How can we use the spectral to find out the maximum displacement for these two cases? So in order to calculate the response here, we need to calculate the natural frequency first. Natural frequency. So what is the stiffness of the frame? thickness of the frame. So that frame, so if we have a rigid floor, what is frequency, stiffness in this case? The key value should be equal to what? Yeah, we should be able to find the equation in your textbook. Right? The rigid floor K value is equal to and that should be in your chapter one. Chapter one.
So it's either 12, 24, or there's a coefficient EI over H3, H to the third.
Yes.
So I need to find out what kind of column it is.
Yeah, so it's a rigid frame. So it's yeah. So the 12 times EI over H could be the one of the column. One of the column. So the key value that's equal to 2 times 12 times EI over HP. That's the key value. That's the key value. So that means we should be able to calculate the natural frequency for each of this building, each of this building. You or this?
It should be 24 EI over H.
Yeah. So now we should be able to calculate the natural frequency. That's equal to 24 times EI over H cubic. So for this two, we should be able to calculate that. So for building on the left, we have the natural frequency, natural period. The natural period here for the left of building should be 2 pi times K over M. So it's equal to 2 pi times B4. Cubic. And the value for the term EI over M is given to us. So that we should be able to calculate the natural period in this case. It's equal to 2 pi times 24 500. So that we can get the natural frequency in this case. The natural frequency in this case. And be equal to that's natural frequency here. Similarly, any questions up to here? Because now as we calculate the K value, we should be able to calculate the natural frequency here. So similarly, we can calculate the natural period on the right. Same equation, but we just use different length here, different height. That's equal to
Thirty-two.
132. 132 to 4 seconds. So that's so based on these values, we can calculate the maximum zero acceleration. The zero acceleration should be equal to either 1g or 0.5g over t. So that means we need to know what is is the value here. In the period here. We need to know the threshold, the two frequency. So when you add 0.5 G over T, that's equal to 1 G. So that we can have the T is equal to 0.5 over G. Here, that's 0.5 second. 0.5 second. So that makes sense? Good. So that means if the period is larger than 0.5 second, the natural frequency, the zero acceleration is equal to 1 G if the natural frequency is smaller than 0.5 seconds. If larger than 0.5 seconds, we need to use a different equation. Something wrong with the equation for period? Maybe square root of K, M over K. M over K, that's yeah, we are calculating the period, not the M over K. So that means that everything here needs to be minus. That's a very significant mistake. That's everything here needs to be a minus. So we need to redo the calculation here. So for the first one, do you agree with me? That mistake? Very. The first one should be the polar building should have a larger period. But polar building should have larger period. Polar building is softer than the lower building. Does this make sense? This makes more sense here. Makes more sense here. Now we should be able to tell the the zero acceleration for the net building here. Acceleration for the net building. So if the acceleration will be equal to 0.64, what is the zero acceleration for the corner building here? Any suggestions? Which equation should we use in this case? 0.5 G over T, 0.5. That similarly, for the right building, what is the maximum zero expansion? Okay, for the right building, which equation should we use in this case? If the natural frequency is equal to 0.98 seconds.
1G.
0.677. I did 0.5 divided by.
So we use the same equation here?
Yeah, point.
No, we do not use. Because anytime if you, yes,
1G.
yeah, 1G, correct, yeah, just 1G. Because anytime if you have the natural frequency smaller than 0.5 seconds, then it's constant. It's constant. So this case is 1G. So, will these two numbers help us to determine the displacement? If we know the acceleration, how can we get the displacement? What's the relationship between acceleration and displacement? So the SD in this case, that's equal to SA over omega n squared. Omega n squared. Yeah, so that's equal to SA over AL 2 pi over Tn squared. Yes, we just go ahead. Meter, that's in meter. Huge?
No, I didn't see the -3 and I was like, oh, that's huge.
Oh, that's negative. So that's small. That's about only 8 millimeters. 8 millimeter is only about 1/3 inch. That's small. Very small. Because building is very. Similarly, we should be able to calculate the displacement for the left one. So we have 1G over That's equal to so the maximum displacement for the left building and the right building already calculated. So what is the gap? What is the minimum gap should we use over here? Did we add those two numbers together or we calculate the difference?
I said we add them.
Yeah,
Add them? Correct. We need to add them because one, we need to consider the maximum displacement is the maximum displacement of the building, either in to the left, to the right, or to the left. Right? So we have one building go to the left, the other one go to the right. We have the maximum. We need to make sure that the gap is larger than that. Is larger than, so the gap here should be equal to so the gap. The gap should be larger than that. So the gap of this two buildings should be about 1 centimeter. Is about 1 centimeter. About almost half inch. Does that make sense? So that's how we use the design spectrum. The design spectrum can quickly tell us the maximum displacement or the maximum acceleration is given for a building. So that's how we use the design spectrum, and the design spectrum is based on the response spectrum of lots of atmospheric reports. So I think that's all about the response spectrum and the design spectrum. And next time we will talk about the response of multi degree of freedom system. When you have a 2-story building or 100-story building, the response will be so different from a single degree of freedom system. So yeah, next time I will show you I will use the shake table to show you some physical table. So probably I need one of you to help me to move because the shake table facility is comes with 2 parts. So if one of you can help me to move the shake table from the structure lab to the classroom here, that would be highly appreciated. Please let me know if you volunteer to just only maybe 5 minutes before the class will be. Okay. Thank you.
Kind of worried about you. And Professor Bioclip, he also didn't give homework last week. Kind of worried about you too, but not enough to email.
We'll work on the project from it.